So we have one last example in this section, and this example talks about what we call a telescoping series. And so when you think about a telescope, you can collapse it down onto itself, or you can pull it out, right? So think about an old-timey collapsing telescope. And that's what happens with the terms in this series, is they start to collapse down. So what we're going to do is we're going to look for a pattern in the sequence, which is going to lead us to a formula S sub k. So look for a pattern to lead to this formula for the sum. So we're going to use partial fraction decomposition. And we have done this previously this semester. Broken things down into partial fractions to make them easier to integrate. So we're going to take that initial fraction, and notice the denominator is a product of linear factors. So I can set this up and say, well, that's a over n plus b over n plus 1. We multiply by the LCD. So my scratch work over here, multiply by that LCD, n times n plus 1 to clear the fractions, and I end up with 1 equals a times n plus 1 plus b times n. And if we use n equals -1 or 0, what we determine then is that a equals +1 and b equals -1. So that sum we have up above, the sum of 1 over n times n plus 1, we're going to rewrite that now. And we're going to say, all right, well, let's find this sum as n goes from 1 to infinity. Now my a goes in there, so I've got 1 over n plus, well, plus -1 is going to make that a minus 1 over n plus 1. All right? So all I did was decompose the fractions. It's the exact same sum we started with. So at this point, now that we have this, it might be interesting to us to examine the terms. So S of k is going to equal, my first two terms, I've got 1 over 1 when I plug in 1, minus 1 over 2. Plus my next term, plugging in 2, I've got 1 over 2 minus 1 over 3. Plus my next term, plugging in 3, 1 over 3 minus 1 over 3 plus 1 is 4. And we can continue doing this forever, but eventually, I'm going to write this on the next line, we end up with 1 over k minus 1 over k plus 1. That's my kth term. Okay, and so what you'll notice is I have minus 1/2 plus 1/2, minus 1/3 plus 1/3. Same thing would happen with my 1/4. There would end up being a plus 1/4 over here. And with my plus 1 over k, the second term in that prior or preceding term would be minus 1 over k. So this simplifies down, and I can say that S of k equals my first term, which is 1, minus the very last term there, 1 over k plus 1. So finding the sum, we want to know if this converges. And essentially what we need to do then is find the limit as k goes to infinity of S sub k, which is the limit as k goes to infinity of 1 minus 1 over k plus 1. And what you're going to notice is when you go to evaluate that limit, you're going to plug infinity in for k, you get 1 minus 1 over infinity. And we all know that 1 divided by infinity goes to 0. So my sum here converges to the value of 1. All right, so as k became infinitely large, as k went to infinity, the sum approached the value 1. And I know I said that was our last example, but I do have one other theorem which we use a bit, and it's the nth term test. So I'm going to skip to the next page. And this theorem here for my nth term test, let's talk about what it means. And it says if we have a sum, so the sum from n equals 1 to infinity of all these a sub n terms, if it converges, then that last term, our nth term, must approach 0. Okay, so, and that's what we've been noticing. These terms continue to get smaller and smaller and smaller and smaller. That's just a common thing. So if we can say, hey, the terms are approaching 0, then we can prove that something converges. Now, it diverges if that doesn't approach 0, right? So we can come over here and go, well, if a sub n does not go to 0, or if a sub n does not exist, then it would be divergent. Okay, so this only works if that nth term, my term way far out in the list, is becoming infinitely small. And an example of the nth term test, here we have the sum from n equals 1 to infinity of n squared. So if we think, okay, what might the nth term look like here? Well, it'd be a really big number squared. And that really big number squared approaches infinity. So in this case, it's not approaching 0. It would be divergent. Let's see. Another example using the nth term test to prove divergence. N equals 1 to infinity of negative 1 to the n plus 1. So in this situation, when we start to look at the nth term, well, we're either going to have negative 1 to the infinity plus 1, which is just negative 1 to a really large power. And depending on whether or not that power is even or odd, this is going to approach negative 1 or positive 1. Because if you raise negative 1 to an odd power, it remains negative. And if you raise negative 1 to an even power, it would turn positive. So again, this is a situation of something that is divergent.